Well, we've been off to a good start with the machine learning special interest group. I think we're full right till Christmas, but there are some open spots in the new year. So if you're interested in presenting, you can send an email to Allison Popple and she can find a slot for you. All right, well, I think we are, there's quite a few people on now, so we'll get started. So welcome everyone. So our talk today is on Hypergraph time series in machine learning. So some graph theory that we'll have today with Sajjad Heydaris, who is a PhD student in the Department of Computer Science here at the University of Manitoba. And so, Sajjad, you joined the University of Manitoba in 2019, is that correct?
Yes, that's correct.
Yes, and after having come from Shahid Beheshti University in Tehran, and so his work focuses on graphs and hypergraph time series, and also machine learning applications. And he is in the complex data lab that is run by Dr. Lorenzo Levy. Many of you will know Lorenzo, who had come as a Tier 2 Canada Research Chair to the University of Manitoba a few years ago, and is in the Department of Computer Science and with a cross appointment in mathematics. So Sajjad, thank you again so much for presenting today. So we'll have Sajjad's talk and there will be time for questions after. So Sajjad will be presenting for around 40-45 minutes, and then we'll have time for questions. All right, so you can go ahead and share your screen.
Okay.
Sajjad?
There we go.
Okay, great.
Right. Can you see it correctly?
Yes, looks great. Thank you.
Right. So thank you for the introduction and thank you for having me. I'm Sajjad Heydaris. I'm a PhD student, as you mentioned. My talk today is on hypergraph and graph time series in machine learning with applications in computational chemistry. So this is done in our lab with Dr. Lorenzo Levy here in University of Manitoba. So let me start by giving you an overview of what we have been doing. So on this slide, you can see essentially what's a sequence of graph over time. So at each of these individual graphs is like a snapshot that we take in time intervals. So and you can see that this graph is changing over time. My research is focused on developing tools and methods to work with these kind of data and with modeling data into these sequence of graphs, and then using various machine learning applications on them. This talk is going to be broken into two sections: the theoretical contributions, which is on state space models for graphs, which is kind of like a Kalman filters for them, and as well as graph and hypergraph neural networks. And for the applications, we will talk about the molecular dynamics and in particular, the prediction of energy in molecular dynamics. So yeah, so let's start and talk about them in detail. A graph, mathematically speaking, is a set of vertices and the connections among them. We usually display them in figures like this, where the circles are the nodes or vertices, and the lines are the connections among them, or the edges, as we call them. As you can see, a graph can convey a lot of information, the most important one being the general structure of it. So the connections among the nodes, and how many nodes they are, how many of them are connected, how they are connected, all of this information. But that's not all of them. We can also store information on the nodes and on the edges of the graph as well. So we have this very simple yet complex structure that could naturally model a lot of different things for us. So the kind of the attraction of using graphs in different applications is that the graphs can convey information that would be harder to convey otherwise. So the structure in particular. And yeah, so let's look at one particular example. Assume we want to work with a molecule that has K atoms, and we want to represent this molecule. There are two different very simplistic ways that we can represent this molecule. The first one being to represent the coordinates of each atom individually. So if we want to do that, we require to have a vector that has 3 times K entries. And this would represent the molecule for us, the atoms of the molecule for us. But there are some problems with this representation, one of them being that the same molecular conformation would have multiple representation. That is, if, for example, we change the order of the atoms in this vector, we would have a new representation, whereas the molecular conformation hasn't changed at all. So we're looking at the same molecule, but we are presented with a different vector. That adds a lot of layers of complexity to our model, so it's not ideal to work with them. The other approach that we can use is using a graph to model these atoms. And the immediate benefit of doing this is that we would have the same graph regardless of the order of the atoms, right? And not only that, but if we don't encode the coordinations and instead encode the distances among atoms, we would also be invariant to translation and rotation. So if we rotate the molecule, we would still have the same graph. Or if we translate it, we would still have the same graph. Whereas if we rotate or translate with the previous representation, we would end up with a completely new one. And the other added benefit is that when we are working with molecules, the atoms usually have a pairwise relations to each other. They are directly connected to each other. And the graphs immediately and naturally capture those relations for us as well. So clearly, working with graphs have a lot of benefits, and they could be useful in simplifying our model, so we don't have to deal with the rotation and translation and the change of orderings. Right. So let me talk to you about some of various different graph time series that we can see and we can work with. To give you an example, we have the sensor network. So these are sensors that are used in forecasting weather, for example. What happens is that these sensors aren't, when we want to forecast changes in the weather, we don't look at individual sensors, we look at the collections of them. And they are often, their values are often considered together to cancel the noise out and things like that, right? So these sensors could be represented on a graph where the related sensors are connected via edges. And we would have a time series if we take a snapshots at maybe daily or hourly intervals. In this time series, what is changing is the value on the sensors, right? So the structure of the graph is stays the same. The links stays the same. We don't add or remove. We want to say these sensors are connected today, but not tomorrow. So they would always be connected. So the graph stays the same, but the values of the nodes changes daily. So that's one example of a graph time series. Another example, which is going to be our main focus for today as well, would be molecular interactions. So as we said, a molecule could be represented on a graph, with the atoms being the edges, with the atom being the nodes and the vertices, and the edges being the connections among atoms. So in a molecular interaction, what happens is that the molecule stays the same. No atom is added or removed, but these atoms will pull and push each other, and they would change their distances. So essentially, if you look at the time series of molecular interactions, we would have a graph that is the same except for the values on edges. So that's another type of time series. And so that the lines would, the distances would change, but the nodes would stay the same. Another example would be working in social media. Facebook, Twitter, whatever, could be looked as a graph where the users are nodes and the edges are the relations among users. You know, if you follow someone, you have a link to them, or if you have a friend, if you're a friend, you have a link to them. And these are more complex than the other ones because we have both creation and destruction of links. You follow someone new, or you unfollow someone you were following before. And also the nodes are added and removed. A user might join or create a new account, or they would delete their account. So if you take snapshots of the network at various intervals, we would end up with a time series that essentially everything on it is changing, right? So so these are some various applications that could benefit from a graph representation, because they are, as you can see, naturally, the graphs would naturally describe them. Now, there are some challenges when working with graph data. The most obvious one is that there is a structural information that we have to process, and it's not always easy to process those information. The other challenge is that the problems usually require us to be order independent. So it shouldn't matter which atom should be considered first or which user joined first, you know, in a very general case. So that's one of the other challenges when working with graph data. And also the most important one is that the graph can have, the graph size can change. And this is particularly a problem because all of the traditional machine learning applications that machine learning algorithms require the application to have a fixed size. And if your input size is dynamic, you know, they essentially wouldn't be able to do anything on that. So so these three require us to have new methods of working with graph data and new methods of processing them. And one thing that the community has been working on since 2014 or before that even, is the graph neural networks. And very broadly speaking, a graph neural network is any neural network that either consumes a graph as input or produces a graph as output, or possibly both. So for example, if you, to give you examples in molecular interactions, consuming a graph as input would be looking at a particular graph molecule conformation and estimating its free energy, which is very useful applications in biochemistry, in chemistry as well. The producing graph as output would be the inverse of this problem. Given a free energy, can we find a molecular conformation that has that free energy, right? This would be the inverse of the problem. Or it could be both. You know, to give you a completely different example, in a social media, you're looking at the graph as input, it can be output a graph that stores the importance of each user in the social media, whatever that importance might be defined as. So these are all examples of applications that could be solved with graph neural networks. And like many other neural networks, graph neural networks have some different building blocks that they are often stacked together to create the pipeline and create the model that we want to work with. The most important of these building blocks for my research is the pooling and convolutions, where the pooling would look at the graph as a whole and try to reduce its size, either to one single node or to a smaller graph in general. And the convolution operation is essentially applying a filter to the graph. So if you're familiar with CNNs, this is essentially the same thing, only when you're working with CNNs, you have your image or whatever you're working with has a fixed neighborhood for each of the data points. So you usually have 4 or 8 neighborhood, whereas in graphs, the neighbor is very dynamic. So one node would have 3 neighbors, while another would have only 2 or 1. So that's kind of the difference between the two. And we will go into details for the pooling and convolution, but there's also attention building blocks that they will tell the network to focus on this particular area of the graph instead of looking at the whole thing. We also have autoencoders, where there's an encoder and a decoder, and the goal is to create a small representation of the graph in a vector. So the model is trained by having the encoder encode to that vector, and the decoder reconstruct the graph. And there are a lot of useful applications that could come out of the autoencoders. For example, compression of the graph, or directly processing the graph through that vector. We also have some generative building blocks that can produce a graph for us from other data points. And we also have a spatial temporal ones that deal with the time elements in the graph time series. So let's look into the pooling. Here you can see a graph in front of me, and each of the nodes on this graph has a vector of size 5 associated with it. So their internal value has 5 different entries. And this particular pooling is looking at the whole graph and applying one of the sum, average, or max operation on them to construct only one vector. So essentially, we go from a whole big graph to one single value. And this is very useful when we want to work, for example, with the free energy that we talked about earlier. The molecule is very large, and we want to work with, we expect to have only one output. So using this pooling method is a very good way of handling that, right? And of course, this function here could be something complex. It doesn't have to be as simple as a sum or average or max. But these are very popular ones in the literature. Another type of the pooling that we see is one that we reduce the size of graph. So for example, we have click pooling that looks for clicks in the graph and convert each click into one node. So essentially, this will reduce the size of graph because you won't have as many clicks as you have nodes. So that will always reduce the size of graph for us. And you can apply it once, or you can apply it until you reach a certain size, or you can repeatedly apply it until you get one node. So you would be you get something like the previous pooling applications. But the point here is that we have pooling methods that just reduce the size of graph into a smaller graph. Right. So that's the pooling one, and the convolution, which is applying the filter to the whole graph, could be divided into 2 general categories. The spectral convolutions, which will look at the problem from a graph signal processing standpoint, and they would use things such as the Laplacian of the graph to apply the filter over the whole graph. And we also have the spatial convolutions, where we won't look at the whole graph, and we will focus on local neighborhoods to apply our filter. One example of these spatial convolutions is the message passing. So consider this very simple graph that has only 4 nodes. Message passing works locally. So each node creates a message and then sends it to all of the neighbors. And in the next step, where the neighbor would also send this node a message, they would aggregate those messages and create a new internal representation for themselves, essentially applying the filter on themselves. So The learnable part here is creation of the message and also the aggregation here. Essentially, using this method, we are passing the information to the whole graph. We can repeatedly apply message passing layers on top of each other to make sure that the information is reaching all parts of the graph. Right. So we talked about, in a very general sense, we talked about graphs and we talked about how they are processed. But let's also look at the hypergraphs. So hypergraphs are an extension to graphs. In graph examples, graphs would capture pairwise relations only, but hypergraphs can capture relations of various sizes, right? So in this example here, you can see we have a lot of vertices, the black dots are the vertices here. And we have hyper edges of size 2, which are the lines. They are only connecting 2 nodes together. We have hyper edges of size 3, which is the triangle here and here. They're connecting 3 different nodes together. And we also have hypergraph of size 4, hyper edges of size 4, which is the clouds here. They are connecting 4 different nodes together. And you can, of course, have a hypergraph of any size. I'm just using a hypergraph of this size as an example, right? So they have the added benefit that they capture relations of any size. But the problem is that working with hypergraphs is even harder, right? So why would we want to work with hypergraphs? It turns out in the free energy of molecule that we talked about earlier, what we are really interested in is delta G, or Gibbs free energy. And we know that Gibbs free energy comes from this formula, which is the difference in enthalpy minus temperature times difference in entropy. And we know that for the enthalpy is defined as sum of all internal energy, which for molecules is defined as this relation. So the enthalpy of a molecule which we want to calculate the free energy would be the energy stored in bond relations, the lines that we saw in many slides ago. The energy is stored in non-bond binary relations, such as Coulomb energy or van der Waals energy. And we also have energy stored in angles, which is between 3 atoms, and energy stored in torsions or dihedrals, which is among 4 atoms. And a graph representation would capture the first 2 perfectly for us. But to capture angles and torsions, we would need to work with, we would need to capture relations of size 3 or higher, which require us to use hypergraphs. Doing this would simplify the model, so the model doesn't have to calculate the energy stored on angle individually. They would have it in part of the representation, right? But as we said, working with hypergraphs isn't exactly easy, so we have to look into ways of processing them. In my research so far, we have used 3 different ways of dealing with this problem, dealing with hypergraphs. The first one is hypergraph augmentation, in which we would convert the hypergraph into a regular graph. And the way we would do it is we would look at any hyper edge of size 3 or higher, and we would create a clique around it. So if you don't know, a clique is a subgraph that in everything in it is connected, essentially. So this blue hyperedge here that is connecting all of the 3 nodes at once would be converted to a single node, and it would be connected to the yellow one, the pink one, and the blue one, right? So that's one way of dealing with it. And the benefit is that if we convert our hypergraphs to graph via augmentation, we can use all of the graph algorithms that exist in literature, and we can essentially, we don't need to come up with new ways of processing the data. We just have to perform the augmentation. The problem is that this isn't a one-to-one mapping, and it's not easy to reconstruct the original hypergraph. So it's not ideal to work with. There is another method of converting hypergraphs to graphs. The hypergraph conversion, where we would create the line graph or the covering graph. There are many names in the literature for it. It turns out this is a very popular concept where you would take the edges or hyper edges in your source graph, and you would create a node in the target graph for it. So in the source graph, we have a hyper edge of size 3, the cloud one. We have another hyper edge of size 3, the triangle, and we have 2 hyper edges of size 2, the yellow and red line. So for each of them, we would create a new node, and we would connect 2 nodes if and only if they share a node in the original graph. So the blue one and the white one, which would be the triangle, have these 2 nodes in common, so they would be connected. And again, we end up with a graph that is much easier to process. And there's another added benefit of doing this, doing them this way, which is we can go back to the original hypergraph if and only if it is fully connected. So if we start with a fully connected hypergraph, we can create a graph and we can do whatever operation we want, and then we can reconstruct the original hypergraph, if it was fully connected, right? But there are many issues with working with converting the hypergraph to graphs. One of them being that the size of this is usually extremely large, and it wouldn't be easy to calculate the Laplacian of them, for example, right? So we would prefer to have ways of dealing with the hypergraph directly. Which brings us to the hypergraph message passing system, which is an extension to the message passing that we saw earlier. Assume we have this hypergraph. Again, each vertex would create a message and send it to its hyper edges. There is an added step here where the hyper edges would process the incoming messages into one and simplify them, and then send the processed message back to the nodes, right? So it's essentially like having 2 consecutive message passing layers together, and this allows us to process hypergraphs directly. So going back to the original example that we had, this is the free energy surface of a molecule called alanine dipeptide. And what we did was we removed this red part from the energy surface, and we trained the model that would, based on all of the other data available to it, and we asked the model to reconstruct the surface for us, right? So the model did this with 99% accuracy, which is a very good measure. It's comparable to other similar things in literature. And the model was able to utilize all of the information that we talked about that was available to it in the hypergraph. Right, so that's part of the research we've been doing. The other part is transferring knowledge from various graph and hypergraph time series. So it turns out there are a lot of time series where we have data for, and there are a lot of time series that we would like to work on, but we don't have sufficient data to train a whole new network for. This is a very common problem in machine learning, as you probably know. It's called the transfer learning. And there are 2 ways of 2 categories of dealing with transfer learning, 2 broad categories of transfer learning. The one shot, which the target domain has a few pairs of training input and output, so the model has a chance of adapting to the new domain. And we also have the zero shots, where the target domain doesn't have any output at all, so the model goes in blindly, right? So in our scenario, we wanted to train the model on a smaller molecule, the alanine dipeptides, which could easily be explored with molecular dynamics. So we could construct the free energy space that I showed you earlier with molecular dynamics. And the goal is to move this model to a more complex one, the 3-alanine model, which is 3 times bigger than the alanine dipeptides. And this makes it very hard to explore. It's not impossible to explore, but it's harder to explore with molecular dynamics, right? And our objective here is to find conformations of molecules that have minimal free energy, or close to it at least. And this is the result that we got using the hypergraphs and some custom pipelines. This is the graph, and as you can see, there should be a size here. The model was able to be transferred to the target domain in a fairly good manner. I think it was 89% coverage. I don't have it. I'm sorry about that. So we were essentially able to use a smaller subset of data that was available to us and convert it to a much larger molecule, right? So yeah, and in future, I hope to keep working on state space models for graphs and hypergraphs, as well as developing cooling layers for hypergraphs with dynamic sizes, and to be able to use both of the previous ones to transfer more molecules and more complex molecules with limited training data available to us. Thank you for being patient and listening to me. I hope it was informative.
Great. Thanks, Sajjad, for that very interesting presentation. And I can certainly see a lot of applications in the health sciences to the work that you're doing on both graphs and hypergraphs. For example, when you talk about what can comprise nodes and edges in a graph, Berit Munchka, who's on this call, a master's student, had been looking at diseases, so chronic diseases, and the relationships amongst them. So the diseases forming the nodes, and then the relationships amongst them, the edges. And so I understand too when you talk about hypergraphs and the value of them, because otherwise you're looking at just pairs of diseases. If you're using a regular graph, as opposed to when you're working with the hypergraph, being able to look at clusters of diseases and the relationships amongst them. So now with your state space models, then you're looking at snapshots in time, and then trying to understand the differences amongst the graphs over time, correct?
Yes. So
yes.
There are many applications. One of them would be to understand the differences. Yes.
Okay, that's great. Are there questions for Sajjad or comments that people would like to make? Can open it up if there are questions.
Can I ask a question, Lisa?
Yes, go ahead.
I just came into my mind based on what you discussed. What's the effect of time interval into your analysis? Because these graphs will change, and they change. For example, if I look at this, every day, so I might see a difference, and the difference will be different if I look at them every 5 minutes or 10 minutes or 20 minutes. Okay. Can you explain a little bit about that as well?
So, yeah. So that's a very good point. So what we assume that we don't really go into the details of how what the time steps are. We just assume that there are discrete time steps. In our case, in the molecular dynamics that I'm focusing on, these are very small time steps, and they don't have to essentially be. They don't have to have the same length of time among them, right? So they could be of slightly various times, but it would be interesting to look into that part as well to see, if we can look at smaller time intervals versus larger time intervals. But I don't have any. I haven't worked on that part at all. But it would be very interesting to look at it. Do you have any example problem that could benefit from this view?
No, but I imagine there are, for example, there are many diseases that at the earliest stage, you don't see many differences between these graphs, but when it actually when time passes, and then when you're at the end of the stage of that disease, you see a lot of progression, for example, in the tumor, in whatever disease that it is. Yeah, I think there are applications, if I'm not mistaken. Maybe Lisa can give some examples
Yeah, absolutely. So I think that this is a really good point in that we don't necessarily assume the same increments. In many health sciences problems, there wouldn't be, Sajjad, the same time increment between what we might want to visualize using a graph. Do you just want to stop sharing, and then everyone will come up on screen? It'll be a little easier to see one another too as we chat. Yeah, so I think that's a really interesting problem in this that Mohammed has raised about the fact that we may not have equal increments of time. And then the other piece, and you've been working in computational chemistry where there may not be data loss, but if we think about individuals, we potentially have attrition of individuals over time. In other words, we lose people. And so that's really a confounder in this, is that it may not be the same group of individuals that will be following over time and that you think about might be represented in a particular graph. So how do you account for that in graph theory? Some really interesting problems. Okay, we'll open it up to others who may have questions or comments. People are still pondering on this and how it might apply in their own work. Well,
I just want to thank you for this. I'm gonna watch it again. So I think I need a second viewing to really digest this. Some great concepts. I thank you very much, and I'll turn it back to Lisa.
mull on that a little bit. Yeah. Well, it is, and I think Barrett and I have a bit of an advantage because we've been working on some of these graphs with, as I said, with chronic diseases, and I guess how to extract that structural information. And Sajjad, have you also thought about the measures of association that you use? Because there are different ways that you can describe the associations amongst your nodes. So what represents your edges, for example, there are different ways to describe that. So can you talk a little bit about the choices that you've made?
Yeah, so essentially, there are two ways of describing the edges. The information that would be associated with edges, they could either be treated as a weight or they could be just a feature set. And for me, from the computational side of it, we would look at weights would have a meaning that if this edge has a greater value than the other edge, it would mean that this is more important than the other one, right? So we would process these differently than, let's say, the feature sets. So let's talk about an example. For example, in a map, where the nodes are places and the edges describe a transport or a road among them, right? You can store the distances as the weights of the edge, right? But you can also have information such as, is this a one-way road? Is this a dirt road? Is there various properties of that road could also be stored and could be important in processing them. And they should be treated completely differently, and there are completely different ways of processing these features and weights. And so I didn't want to go too much into the technical side of it, because I thought that would be boring, and we would just have to look at equations all day. So yeah.
Yeah, and that's something that you haven't represented yet. And just, I mean, some of the diagrams you were presenting were very simple, but there are ways to visualize that too, as well, the weights. And also, when you think about the nodes, the size of the nodes can be varied as well to present a visualization of how large, for example, when we are looking at chronic diseases, the prevalence, in other words, how common a disease is in the population, could be represented by the size of your node. Yeah, and then the edges representing the strength of the relationship, or as you said, the weight between them. Okay, are there any other questions or comments that people would like to make? There's a few comments in the chat here. I hear nothing at this point. People are still processing that. Okay, so I'll ask one more question just about then the structures of your graphs then are what you can use as inputs then to your machine learning models.
Yes.
And then you're doing that, really what you're doing then, Sajjad, is at separate points in time, you may be building separate machine learning models at each of those points.
So we would build one machine learning model that would process all of the points. So we wouldn't create individual in the application that I'm working on. We wouldn't create individual models. We would create one single model. Yeah.
And so part of it would be with your machine learning model to look at the changes across the graphs over time, so that those become inputs into your machine learning model. Is that correct?
Right. So
Okay.
as we talk, like for example, in the free energy part, we are interested in delta G, or the difference in free energy. So one way of looking at it would be to look at two different molecules, two different conformation of the same molecule, and look at the difference among them and see how that would affect the free energy. Yeah. So that's one way of looking at it.
Yeah. Okay, that's really fascinating. Thank you so much.
Thank you for having me on this.
Yeah. Okay, unless there are any other questions, I think we've got a little bit more time, but I don't see any questions that are popping up.
Yes. Hi, everyone. Can you hear
Hi.
me?
Yes.
Yes. Sorry, I had to switch on my private computer because I couldn't access the microphone on the public one. Thank you for the presentation, Sajjad. It was kind of interesting on the operation part, where we modeled the graphs with networks and pooling and filter operations. Yes, convolutions. I'm not quite familiar with these operations, even if I learned the graph theory, general graph theory during courses. And I was wondering if there is a way to represent graphs with their adjacency matrices, for example,
right,
where you have multi-dimensional links, where it could be the weight between nodes, or like the number of connections between atoms. Let's go back to the molecule example. We could imagine temperature, I don't know, but is it like the kind of convolutional operation on such matrix, like adjacency matrix?
So what you're asking about would be the spectral convolutions. They would deal with the whole graph at the same time, right?
Yes.
we didn't cover them in this presentation, but yes, there are many. And what happens is that they usually work with the Laplacian of the graph, which has some is a pretty similar definition to the adjacency matrix. But there are some properties to the Laplacian that would be more helpful to us. So essentially, the Laplacian would describe for each two nodes the probability of moving from one of them to the other one. So that's what they're describing, which is a very similar concept to the adjacency matrix, but you would just show your possible the things that you could go to. But the Laplacian would also capture the weight that we talked about, right? They would be captured in that matrix. And the spectral convolutions use that Laplacian to do their calculations. Does that answer your question?
Yes, it's quite interesting. Actually, there are many. It's a very wide domain of applications, graph theory plus time series. I studied time series as well during my master's degree. And I was also wondering about forecasting or like trying to find patterns between time points, especially like seasonality or trendings on the graph behaviors. So I was wondering what kind of examples could we extract from such data? For example, the number of nodes evolving. Are there some specific ways of forecasting an outcome based on the graph shape? It's quite complicated. I don't know if you got the question, but
yeah. So for forecasting, you have to limit your what you want to do. So because it would go out of hand quickly. But if you, for example, look at the social media one, or recommender systems, they could be described as a link prediction, right? So I'm not sure if you're familiar with them or not, but assume you're in a sales situation. You have your users, and you also have items that the user would buy, right? And you can create a graph out of this where the users are connected to the items that they have previously purchased, right? And one forecasting problem would be a link prediction, essentially. In future, this user, which link is going to appear for this user? And can I find them before he does, and can I suggest them to him so that he would be more interested in buying them, right? That's one example.
Yes.
Same thing in social media. But another completely different example would be, if the graph was staying the same. For example, in molecular dynamics, we have a trajectory of the molecular interaction, right? So as I said, the atoms in molecule are affecting each other. The forces are pulling and pushing each other. And we have this trajectory of a molecular interaction. So we might have data up until a specific time, and we might want to know, okay, how does this continue afterwards? That would be another forecasting problem, right?
Yes,
but
exactly.
In that, your graph is staying the same, but other things are changing. There are other examples where you also add nodes to the graph, like graph edits, for example. But it would be. I think they have some application in urban planning. I'm not really an expert in that area, so I wouldn't.
Okay. Well, thank you for the clarification. It's very interesting domain.
Yeah, it is very, and you can see the numbers of application areas that there may be. Great. Okay. Well, I don't see any other questions that are popping up. Sajjad, thanks very much. Well, no, I have one more. When we talk about validation of of a machine learning model, for example, so when you're thinking about validation, so you're building these graph structures, are you sampling? Can you sample the structures themselves, or are you sampling the observations and then building the graph structure?
So the application that you're working on has a benefit that we know the exact graph, right? Because it's not gathered from any experiment. It comes from a simulation,
Okay.
right? So our colleagues perform. I forgot the name. There's a simulation that simulates how the molecule would react, and they would store them at various points, and that's the graph that we work with, right? That they would form the trajectory. So we have the full data available to us. But I could see that in other problems, in other scenarios, you might have missing data, and things could. You might have to verify the structure of the graph. I don't know how you would approach that, though. I haven't really thought about it.
Okay, so that's an open problem. Yeah.
There might be something in the literature. It's a very broad thing, but I haven't studied it.
Okay.
Yeah.
Something for future in your PhD, right?
I would look into it.
Okay. All right. Well, thanks. If there's nothing else, then our next talk will be on November the 18th. So normally we would be meeting on November the 11th, but that's a holiday. And so one of Ridwan Sanusi will be presenting on November the 18th. And we're looking at random forest, we're looking at tree-based models for looking at patient-reported outcome measures. Okay, Bill, anything to add?
No, thank you. Stay well. Really appreciate all the participation, and great to see.
Yeah, thanks again, Sajjad. Great talk.
Thank you.
Appreciate it very much.
Thank you very much.
Bye, everybody. Yeah, bye.
Bye.